Okay, good afternoon, everyone. Thank you for joining us for our October JK webinar with Professor Mohsen Yahyaei. He is the director of the JKMRC Centre, and Professor Yahyaei is an expert in modelling, optimization, and control of comminution circuits using novel approaches and tools. So I'll hand the stage over to Mohsen, and yes, thank you, Mohsen.
No worries, thank you very much. Thanks for the nice introduction. And I keep the chat open. If people they had problem with the voice, just please let me know. And thanks for joining the session today. So I'm going to talk today about process control for mineral processing plants and why people like myself as metallurgists should know about it and why they should care about that one. So this is kind of a talk that actually I've been doing it a number of times, but every time I'm doing it from different angle. So if you have been in one of the previous webinars run by JK Tech or other groups, so although the title is very close to what I presented before, but the content is not as basically similar. So it's going to be different because every time I'm tackling different angles. Before I move on, I would like to acknowledge the traditional owners of the land in which we meet and essentially pay our respect to their ancestors and their descendants, continue their cultural and spiritual connection to the country, and recognize their valuable contribution to Australia and global society. And I think it's very important, again, I'm doing this in every talk that I do as professionals. Although we are looking into and thinking about professional aspects of our projects, always have in mind the greater impact that some of the work that we do has on communities, societies, as well as environment that we are operating with. And it's very, I think, important for people to recognize the culture that actually exist within the area that they are operating, and they try to understand and learn from them. So everywhere that I go in the world, because of my role, I have the privilege to travel around the world. I recognize actually they are very rich, basically civilization and culture that actually by understanding them and learning from them, we can improve most of our professional practices. So I would encourage all of you guys to think in that level and basically be sure that actually you utilize some of that knowledge as well. Cool. So I think just a bit of a background for people that they might not know me, which explains why I'm giving this talk. So I'm basically mining engineer by training, focusing mineral processing, but also I hold an MBA from the University of Queensland for business management, and also I'm a chartered professional and registered professional engineer in Queensland. My main area of research is process automation, and that's where most of my research exists. I'm part of Sustainable Minerals Institute, SMI, at the University of Queensland, currently director of Julius Krasnich Minerals Research Center, JKMRC. And also I'm a program leader in SMI, looking at a program called Future Autonomous Systems and Technologies, FAST. And I've been working in operations as well, and also being researcher and academic, but pretty much my work is primarily applied. So you can see some of the area of the work that I normally do. I'm pretty much a practitioner, essentially working in different fields in the industry. I have a chance to travel around the world and visit many of the operations and work on site. So that's one of the key points, which I think when I work, essentially I bring that angle of practical aspects into my discussions and talk with the industry. I wanted to give you a quick overview of JKMRC as well. Over the past couple of years, we pivoted JKMRC as one of the strong research centers that it has expertise in comminution, classification, and flotation toward what we call a transformational processing solution. Essentially, through 5 research groups that we have, we focus on novel separation technologies, surface chemistry, high temperature processing, as well as process automation and control, and energy transition and decarbonization, which becomes one of the important aspects of the industry in recent years. We work through partnership with industry as well as essentially solutions providers, and also we can identify some of the solutions for ourselves when there is a gap, and we develop them. One of the key areas that we focus is essentially development of graduates that become the future workforce and future leaders of the industry. And also we are very much engaged in skill development and knowledge transfer through our professional development courses and occasions like these webinars that actually we try to disseminate the knowledge and capability that we have. And we've worked pretty much through that partnership with basically industry to make sure that actually we can transfer the novel knowledge that we are generating through our cutting edge research, so all of the institutes, they can use them. I am privileged to actually work with a great leadership team in JKMRC. Associate Professor Kim Ronge, who is the group leader for separation group. Associate Professor Lisa Forbes, who is looking after flotation chemistry group, and Dr. Jadon Ma, who is a group leader in high temperature processing. So those are basically top experts in the field in the world, and they are running most of our research in those fields in JKMRC, and I have the privilege to work with them. Also, all of these great research comes with the help of a large group of research team. You see some of the names and figures in here and pictures here that actually they are engaged in those research works, and these are the great minds behind some of the solutions that we are developing and offering to the industry. And to the same level of importance, we have our research team students that actually they are some of the major drivers of those key areas that we have to develop the fundamentals to get to the point that actually we can develop solutions. And these are basically the cohort that actually form the future leaders of the industry through the experience and knowledge that they gain through the work that they do in JKMRC. Also, every institute needs a great support of the administration team through workshop, lab services that we have, as well as the administration services and safety aspects. And I think they play a key role in terms of ensuring that our research are progressing very well. And I would like to acknowledge their contribution as well. Okay, so I want you guys, we got already around 20 participants, to engage with this work, because when I'm presenting it as a webinar, it's very hard to interact with people, but using your mobile phone and scanning the QR code, you would be able to get to a questionnaire that actually I have, and I want you to engage with the questionnaire and help me with the question. So, sorry, I'm going to go back again quickly here. The question that I have is, what is process control in your view? And there is no wrong and right answer. All I want you guys to do is, is to rank these based on the level of relevance that you see they have for process control. So you can just simply use your mobile phone, scan the QR code, and I can see that there is already one participant there, and try to rank them. So you can rank them from 1 to 4 based on the level of relevance that you can see they have to process control. So we can look into them. I put 4 options there. Essentially, some people might think stabilization of the process is important. Some people, they might see monitoring and managing, prediction and optimization, or overarching optimization might be something. So great, we can see results of 1 person. I'm hoping that actually we get at least 18 people joining that poll. Okay, good, very good outcomes. It seems that the monitoring, managing, and adjusting the process is a winner so far. We got 5 participants. Let's get more people. And this is anonymous, so make sure that actually you join. And that gives us a bit of a view in terms of what do you see as process control. And again, remember, this is essentially, there's no wrong and right answer. It's more about your view, how relevant each of them are to the process control. And you would basically see that actually all 4 of them are relevant, but for me, it's more about gauging in the audience, how do they see the level of relevance of each of these aspects. And it's good that actually we can see a good level of engagement from team. And thank you very much for participating. So far, monitoring and managing still is a winner. Then people, they vote for prediction and optimizing process condition. Very close to that is optimization of the process holistically, and stabilizing the process to achieve desired operation. It seems that it is last, which is kind of a bit of a surprise for me, because usually that's the one that actually comes either first or second, but it's a good outcome. So it means that actually most of the audience, they think process control is about monitoring, managing, and adjusting the process to ensure productivity. Then prediction and optimization of the process to increase the throughput, which is obviously is important for the mining industry. And then optimization holistically. And then the last one is the stabilization, which is a good point. So the poll is going to be active. If you didn't manage to answer, you can do it afterward. So I think, as I said, pretty much all of them are relevant, or they are aspects of process control. Whether it's the stabilization of the process to desired operating condition, which later you will see that's the base layer that actually we want. And then monitoring and managing the process to ensure productivity as well as the throughput are the ones that actually they have effect, and then they stabilize and then optimization of the system holistically. Cool. So in terms of automation, I think there's a key aspect. I mean, I think most of you who are working in operation, you're aware that actually there's a strong push from our industry to get to advanced control and automation. I think the big driver behind that is the drive that we have for producing products that it comes at a lower cost with high productivity, which essentially primarily is driven by the increased emphasis that nowadays we see on environmental, social, and governance aspect, in particular the energy transition as well as the social performance. And how automation actually delivers that value, I believe that actually it's through efficient use of resources, improving the product quality, enhancing the safety and the work condition, and also reducing the losses. So that's how essentially the automation and control, they can provide that. But to achieve those values, the key or the way that actually you can achieve those values is through coherent and cohesive decision support that is backed by automation. And I think that's one of the key points that I want to people to pay attention. Process control or process automation by itself is not going to deliver the value unless it is helping and supporting a coherent and cohesive decision making. And I've been in a couple of conferences in the past few months around digitization and advanced automation. And I've been doing some workshop with various companies around that automation. And I can tell you the number one problem I can see, or the challenge I can see, is all of these great solutions, especially around automation, real-time prediction and optimization, are developed in platforms that they are completely separated, and pulling all of them together in a coherent decision support system, it's one of those major challenges, because at the moment, the bulk of the solution, not all of them, but the bulk of the solutions actually primarily focused on unit optimization or unit process monitoring and optimization. And often the directions of the changes and optimization are not coherent across the whole processes that you would see. And I think that's a key part in terms of automation and the control can deliver that value through enabling that coherent and cohesive decision making, which is essentially the crux of the value that we do. When I'm talking, you see that actually I use two terms, process control and process automation. People often, they use them interchangeably in terms of when they talk about process automation, often they talk about process control, or when they talk about process control, they talk about process automation. But there's a subtle difference between these two aspects. And that's primarily around the time span the control happens. So when you think about process control in a context of a mineral processing plant, which I presented in here, a typical SAG mill, ball mill crushing circuit, which commonly known as SABC circuit. It's a circuit that actually is essentially used widely in the industry. The process control essentially is about collecting signals, passing them through the control room, and then using basic level of control, which is stabilizing process control to a target, with a decision that is made by operators in terms of where should be those targets, or often interaction and intervention of the operators to adjust the targets to get the process to that level of stability and the level of performance. But when you think about process automation, it's pretty much about moving that decision making essentially more toward automation, which means that actually most of those decisions around the levels of automation, the levels of the targets that you have or the set points, and basically interaction between units is made autonomously by algorithms that you have developed. And then the operators are more looking into setting targets, setting boundaries, and also moving direction. That level of automation actually looks into more like a longer term intervals as well, versus the process control. So I think I needed to clarify, when I'm talking about process control, I mean that aspect, and then process automation is a different meaning in my presentation. But what I found is often you're very good in our industry to confuse words or misuse words. And that's one of them. Essentially, when they talk about control, sometimes they mean automation. And sometimes when they talk about automation, they mean control. So we have to be careful about that aspect. And obviously, we are dealing with not a few data. It's essentially a huge amount of data that you have to read, evaluate, and then assess, and then make that decision. So when we want to move toward process automation. Essentially, we want to change the landscape of the decision making. So if you look, this is I think, again, it's an overall view of a process from the mine all the way to production. And then what I have done in the left-hand side graph, I created a kind of a typical structure for where the decisions are made in a typical mining operation, and the time span that they have for making those decisions. So there's a term called time span of discretion. Is the time that they have effectively to make critical decisions with that time frame using the information that is available. And then in the y-axis, what I have done, I put the number of people that they are in that level and making decisions with that time span of discretion. So in a typical operation, normally you have a more number of people at essentially on the ground next to the operations, that they are operators, that they look at the results of the measurements and the data that comes from the process and make critical decisions. And usually the time span that they have is in the order of seconds and minutes. So they don't have much time. So normally when you're sitting in a control room, you have a couple of minutes and often a few seconds to make a critical decision in terms of, should I turn on a pump or turn off the pump? Or should I increase this set point, or should I decrease it? So those are the things that you have to do. As you go higher up the chain, you've got more times to make those critical decisions. But the key point in here is often, and that's what we don't normally pay attention, is many of those decisions that is made with short time span of discretion, which is primarily around the control of the process, which means actually you look at the process, set the target for the set points or set the boundaries for the process, are made in the order of second and minute with minimum amount of information that is available, which is about the sensory data that you have. And they have a significant impact in the bottom line of the company, but it takes a while for those to be seen at the higher level. So, and we think actually we can start moving that level of process into through automation of process, we can improve them. Sorry, through automation of this process, we can improve them. So when I'm talking about control, the first thing that we have to bear in mind is the control has levels as well. So what at the basic level we want to do with the control is we want to stabilize our process to achieve a target. The target could be a desired product, or it could be a certain outcome from the process, in light of the variation that happens, that I categorize them into 4 groups. The variation that relates to methods, variation that relates to the environment, variation that relates to equipment, variation that relates to human being preferences, which essentially tends to create fluctuation to the process and take it out of stability. So the example of the SAG mill is a great one. I take that because most of my time I've worked with SAG mills and I love them a lot. So I get that basically example here. Although there are many people that they want to retire these SAG mills, but I don't think they're going to do it any soon. That's fine. So essentially, when you look at the SAG mill as a process, you got the ore and water coming as an input into the SAG mill. You are looking into your product quality, the throughput that you can get from that SAG mill, the load, and also the power draw that you might have as a result of the operation of the SAG mill. In light of that, actually, the objectives for the targets might be parameters that actually has effect on SAG mill and it might fluctuate it. We know that actually ore has variable property. The fluctuation in upstream units is going to have effect on your mill. The equipment itself, because of the wear, for instance, the liner profile are changing, the grade aperture size changing, and that actually changes the behavior of the mill. And also because these devices are controlled by human beings, the operator preferences are also one of those aspects that keep changing those processes. So when we design stabilizing control, essentially we have a system in the background that actually measures some of the critical parameters of the process, checks those against the targets that often is set by operator, and then generates control action that actually manipulates some of the parameters in the process to ensure that the process is stable. But the nature of the stabilizing process control actually is a passive approach. Essentially, unless there is a deviation from the set point, the process control is not going to take any action. So those actually is done through often localized set points for each process. And the set points are often used for setting or achieving a target performance or ensuring the safety aspects, like for instance, the equipment, if it's work under pressure, it's within that target, there is no spillage happening or some of those aspects, or also managing the environmental aspects. Usually those stabilizing controls are disconnected from other units, except when there is an interlock between units that actually might do that one. And usually they are single input and single output. But they are foundation for other levels of the control. Without them, actually, we can achieve the other levels. And then the prime example for those stabilizing control is done through PID controller, proportional, integral, and limited controller. But there are other approaches like novel approaches like fuzzy logic and AI as well that they might basically help. So the other level actually is, one of the aspects that actually I want to say in terms of how we can move from process control, which is stabilizing, to automation. When you implement process control, that brings precision and repeatability. So because one of the key aspects of the control is when you set your system, they are precise. Essentially, they react and respond to the system, to the changes, the same way every single time. And that's the beauty of process control. It brings precision and repeatability. And if you look at the graph in the left-hand side, in this graph, actually, I'm looking into the capability of machines or algorithms that they make decisions versus human in the face of uncertainty. And you can see that actually machines are very good when the uncertainty is low, especially when there are levels of skills or rules are included. As the uncertainty increases, that's where you need knowledge and expertise, which humans are very good at that part. And what we think actually is, because automation or process control can bring precision and repeatability, we can reduce uncertainty and start driving a pathway toward using algorithms, automated algorithms and machines to make those decisions automated. And that's where the supervisory control or model predictive control can perform very well. So essentially, once you established your stabilizing control as your base layer or the foundation of your advanced control, then you can actually implement supervisory control in there that actually that uses the prediction of the process, identify what are the key aspects that is going to change in the process, and it can actually then drive the stabilizing control toward new targets. And this is quite a bit of an active approach. Essentially, it predicts the process status and set points, and then use an active approach to control the process. And through that, essentially, what we do is we use the model predictive control, or a term that actually we coined it as model-informed process control, which means that actually the models are not heavily involved in controlling, but they inform operators in terms of making decisions when your models are not as well structured or are not very trusted. Still, they are essentially looking to separate units and use the information for that, but they can provide an overview of the process as well. And they normally incorporate upstream and downstream as a way for adding constraints. Those models that you use, it could be semi-fundamental models or even fundamental models if they are existing. And another approach that is data-driven approach, sometimes they use artificial neural network or any other machine learning techniques that they are heavily rely on the data as well. So those are the techniques that they are commonly used in the industry. The last level, which is essentially moving toward more advanced level, is about optimization. Essentially, what we put as one of the options there in terms of not only focusing on units individually and trying to control them, but also focus on holistic optimization, which means that you bring constraints from the process and then pose those constraints either directly to your stabilizing control through target that you add, or you impose them to your MPC, model predictive control, for making decisions in supervised control level. So that's something that you can essentially organize and do. That's essentially the process. So, and the optimization control, essentially what it does, it moves from centralized unit-based essentially toward enterprise control. So essentially, you are not only focusing on unit processes in your processing plan, but also you are thinking about the constraints that might exist in mining, or the targets that you might have in your shipping, or the requirements that it has in your smelting. And then you can actually look at the overview of the value chain, set the holistic KPIs that actually it can translate between all of the units, and then use those KPIs to set constraints and targets for different basically operating units, and then through that you can trickle it down to even processing units that actually they can look at. So when you do that aspects of automation, essentially that can change the landscape, and it can help you to start moving from process control to process automation. What does it mean? Essentially means when you start implementing control, through that precision and repeatability that it brings, it's going to reduce the uncertainty. And that means that actually then you can start basically having models and tools that actually they can perform very well when the uncertainty is very low. That means that actually now I can start automating bulk of the decisions made in the short time span of dispersion, in order of seconds and minutes. And that essentially, it can change the landscape of the population of the people that they make critical decisions in your operation. And as you can see, what I've done essentially, this is essentially is my view in terms of when you implement automation, how it's going to change. So essentially, you're going to have a group of people, which could be essentially your operators that they are moving from that level of decision making to this level, which means that actually I call them constraint management. Essentially, they use the human intuition in line of the areas that actually has more complexity, which requires knowledge and expertise. That's where human actually has more skills. So to understand the constraints of the process, and then trying to, by managing those constraints, let the automated system to achieve its maximum potential for automated decision making. In that sense, then your operators, they're not going to be much worried and concerned about making basically critical decision of seconds and minutes, which often is not very consistent. You rely on their expertise and you rely on them being able to process and analyze huge amount of data in a short time span of time to make a decision. So bulk of that can be done by automated systems when we develop them. And that's primarily because your control system brings precision and repeatability and reduces the uncertainty, which enables that ability. And still, obviously, you will need operators there. And I don't see in the near future you're going to have fully automated plants that actually they don't need any operators. But it could reach at that point that actually you won't need them at that level. But in my view, actually, probably is less costly and faster, essentially, pathway if we develop an integrated system that actually human and automation can work hand in hand. But then you can use human where they are much, much more good at and the experts, essentially identifying constraints by analyzing some of the aspects across the whole process. They're going to have more time in that time span of discretion to make those decisions, reallocation of resources, setting new targets, identifying potential, essentially, must constrain and start releasing them, which then helps the automated system to work with much, much less number of limitations. But as you heard, that is heavily rely on the automated system to be precise, but at the same time, it has to be accurate as well. Okay, and that I think is one of those major challenges. That actually, if your process is not accurate, even if it's precise, it's going to basically be a problem. And there is a pattern for that. Essentially, most of the automated systems or controls that you apply, inherently they are precise, but not all of them are accurate. And probably if you have experience, you would see that actually in many operations, when they start implementing a new systems that it's controlling, it is a bit of an effort either beforehand or implementation, or even after implementation, to be able to essentially look at it, keep updating it, and then make it more and more accurate. Why accuracy is important, how the accuracy is going to be achieved, I would essentially put it in this form, in terms of if you look inside an automated system and say how it works, essentially I divided it into two forms, which I borrowed it from my colleague, Professor Ross McRae. I didn't really like this system. So when you think of automated system, the automated system actually has a part which is called sensorium. The sensorium actually gets input from the environment to generate what we call it situational awareness. And that situational awareness with the targets essentially feeds into a decision planner to create commands that actually then convert into action to the process. So why that process essentially becomes important in terms of being accurate. I mean, this is a book that actually I really encourage everybody to read it if you haven't done it. So it's freely available on internet. So you can just scan the QR code, you can get access to the book. And the book essentially what it gives you, which I liked it a lot, was essentially evaluates how us as human beings judge machines when they make decisions. And when I read that book, I realized actually why accuracy in our automated system becomes important, and why many of the automated systems that we have in industry, they are not working at their full potential. That all comes into the issue of trust. And the trust actually, the bulk of that is relying on accuracy and precision. So precision is the inherent property of control system, but accuracy is not. And when I read this book, I realized actually human being is willing to give control to machines or algorithms when the accuracy of the decision that is made by those systems to a great extent is higher than a human being when they make the same decision. So essentially, if you provide information to a machine and a human to make the decision, so human being is going to basically trust the machine more when the level of accuracy the decision is made by a machine is higher. And in many of the cases that they reviewed, it was around 60% more accurate. It means that actually the system has to make 60% less mistake comparing to human to be able to be trusted by us to take it. And essentially accuracy of the information and the accuracy of the decision that is made, which essentially relies on accuracy of information, is the biggest driver that we need to have. And to me, everything starts with good measurements. And that's a key part. Remember, again, the whole system of autonomous system. So when you make decisions in your decision plan, one of the key inputs actually is your situational awareness. And having wrong data and essentially those information, it's the key part in terms of making wrong decisions. So therefore, the trustable system actually starts with measurements that actually provides you with information that it can help you to get that. To get that level of essentially accuracy in your decision. Obviously, you need good decision planners as well. So with good data and wrong decision planning, you're not going to achieve the accuracy. But in my view, actually, it's much easier to develop those decision planners through understanding of the process that we have. But when the data are wrong, it's very hard. So, and we should focus on that a lot. So let's go another poll. And let's look into how everybody think. How much trust you have to the sensors that actually you have in your operation. And I just divide them roughly. I mean, I don't need you very accurate data, but if you very much trust your sensors that you use in your operation, put them more than 90. If you trust them a little bit, 70 to 90, less 50 to 70. If you don't trust them that much, put it 50%, and you might not already work in operation. It's fine. You can say that actually I don't work at operation, so but still you have that participation. Okay, at least we got some people that they have more than 90%. That's very good to see that they have trust. So cool. So I think this is very important for me. Make sure that you participate as much as you can. And got around 25 people, so it's going to be good to get more participation there. But it seems that actually 70 to 90 is the winner. So we got level of trust, but it's not very high. But it still is good to see some people that they think actually they have sensors and that they can trust them more than 90%. And I can see that actually there are operations that actually they don't have that level of trust in their process. But it's good that actually there's nobody thinks actually is less than 50. Good. So, but you know that's a key part. As you can see, when you have that 70 to 90% trust, that means that actually there are times that actually those sensors they are not providing you with right information, and that essentially then feeds through your decision making. And then when automation system makes decision based on that, it might end up in problems. And you know, the level that we are operating in operations, if some of the decisions are made based on wrong information, it might end up into catastrophic events. Like I've seen a number of cases that the system, the automated system that actually they had for running the SAG mills resulted into bogging the SAG mill. And that essentially cost the site 1 to 2 days of operation because they had to shut down the plant, dig out the SAG mill to be able to run it again. So the level of consequence that some of those wrong mistakes is going to have is huge. And therefore, we need a great extent of essentially confidence in the data that we have to be able to trust. So, and we know that actually the control system, because it uses control to stabilize the process, which relies on essentially stability of the input or stability of the equipment or stability of the equipment condition. So essentially, the decision that made for any of these aspects has to be based on correct data sets. And for making those decisions, essentially, we got many of the aspects of the process control system that actually we have to rely. They have to work okay to make sure that you get reasonable results and reasonable actions. And that essentially starts with instrumentation, the sensors, the measurement that we have, and then your final control element in terms of when you set an action, whether that actuator actually got to the point that actually you wanted. And then obviously the decision planner inside, which is your control logic behind the back, also has to be reliable. If it's in a stabilizing structure, then the PID controller or any of the type of controller for stabilization that we use has to be well tuned. And if it's not there, then it's going to be a problem. And then you got a whole support system around the system, like programmable logic controller and distributed control systems, to ensure that actually all of these units are coordinated, they're interacting, and they're working together. And that has to be functional as well. So there's quite a bit of a work that needs to be done, especially, and that's, I think, one of the key points, especially at the stabilizing control level. Because, as I presented earlier on, the other levels of control, they are heavily rely on that stabilizing control. And if you don't have that level of control, then essentially the base stabilizing control working, then even if you have the most advanced models as your MPC, because without that stabilizing control, you're not going to get there. And that's, I think, is one of the issues that I can see again in the industry, because there's a strong push at the moment for digitization and advanced control. But people often forget that actually we have to make sure that we got the foundation right before we implement that. And some of the people or vendors, they might not even think about that level because their role is actually selling those advanced technologies. But I think that's very important, at least for people that they are working in sites. So for us as a research entity, we have been focusing in that problem for a long time. And I think we are developing research that I would like to, for the next couple of slides, to explain them, how we want to leverage that capability to help improving reliability on the data, ensuring the quality of the data, and start providing that insight for control system. So one of these works actually is a great work that one of our PhD students have done, Niranjan Adhikari. He also presented this work in SAG conference in Canada a few weeks back. And he has been working on how we can actually fuse the models, the domain expertise, and the power of data analytics together to be able to assess the data that is generated by operations and be able to identify them in form of operating regimes. And this is a prototype of a dashboard that he created essentially based on the work that he has done, that actually by looking at the 1 year worth of production data from 2 operations, he essentially worked with experts, start isolating the data, identifying different operating regimes, clustered those data into those operating regimes, then checking them or sense checking them with domain experts to make sure that those clusters are meaningful, and then use that algorithm, clustering algorithm that was trained through fresh data, which then it can identify things, for instance, like whether the operation is a steady state or not, whether now it's facing hardness constraint, or whether it's facing overloading issues. And the beauty of that actually is now every time basically series data that you have, you can actually start stamping them with conditions, or in near future that we are working on that one, also with the confidence on the data that you have. And that essentially, it creates a pathway for us to try to be able to automate most of those transformation of the data to useful information, essentially in that form. And this is kind of a view that we have in terms of once that is established, then essentially in an operation, you might be able to start adding labels like these ones, that as the data is generated, the algorithm behind the back that is trained, then start essentially using that to identify these situations in terms of what's happening in different states. So that's essentially, to me, it's a very great way of visualizing what will be the end results of what we are developing at the moment. The other one that actually is something that we have been working on that one, and probably if you have been listening to my talk, probably you're by now sick of me talking about subsensors. Subsensors actually have a great opportunity to leverage the knowledge that we have developed from processes to reuse all of these huge amount of the data that is generated by operations and turn them into useful information. And our approach in JK was actually, we are happy if there are lots of hard sensors introduced as well, but we are thinking actually already we are generating huge amount of data. Let's use them. And we essentially developed a suite of soft sensors now, and we are very proud of JK Milfit, Now we have JK Cyclops as well. We have a stockfire sense, and soon we're going to move into, and we got a V-mill feed that actually is developed as well, and soon we go to other areas as well. And that actually, the idea is they can use not only to provide insight that they are more important, or the data that are more important for control, but also there is another essentially value for those sub-sensors. They can actually evaluate the data integrity and the accuracy of the measurement through sensor fusions. And that's very, very valuable approach in terms of, remember that I said the data is the main input. So how you would make sure that the data are, the integrity of your data and the accuracy of the data. Sub-sensor is one of those pathways. It can help you to identify that. So the JK feed actually is one that actually I'm very proud of. It's a soft sensor that we have developed. It comes in any platform that customers they require. We don't sell a platform. We can put it as simple as the Excel file that they want to use it, or code it into their DCS, or code it as an executable, or put it in any other platform that you might use, the platform of choice. Already is installed in 22 installation as of August. Already we have 6 on the since then. 18 SAGMIs, 2 AGMIs, and 2 BOM is already done. This is showing the level of accuracy of the prediction of that tool after the first installation. It doesn't require any further installation when you do that, unless you change your line of design. And these are the measurements that are done by site, not by us. And essentially fairly accurate, less than 0.5%, where in the region that actually most of the operations exist. Recently, actually, we have been privileged to work with one of the operations, and actually I'm really grateful of them for trusting in us and giving that opportunity to us. We developed a sub-sensor for cyclone. We call it Cyclops. And that actually gives you a real-time view of what's happening in your cyclone around the circulating load, by size, and the PAT of the cyclone. And also it can provide you indication of roping. One of the value of this sensor, when I was talking with my colleague Marco Hilden, who is the brain behind this work, the beauty is when we looked at the site particularly, there were occasions that they didn't have this the density, or they didn't have the flow rate because of the sensor issues. But the sub-sensor, when it's trained, actually it was able to fill in those times as well. And that's another value of sub-sensors. We can actually fill in the sensors data when they are off calibration or they are not working, which is very useful. And also we got basically a vertical mill fit, we call it V-mill fit, that actually we are developing, that actually help us to understand the product size and circulating load. And that's very valuable for real-time monitoring, especially around regrind processes. The cyclone actually can be done for primary cyclones or secondary cyclone, doesn't matter. And the V-mill fit vertical mill, if you use it as a tertiary or regrind, we can use it as well. And those sub-sensors actually, they're going to provide you more trust in your data. And I think they're going to pave the road toward that automation vision that I had. And 2 more slides before I go for questions. One of them is actually now we are looking into those essentially other areas as well, because nowadays you can see that actually these, what I call them mobile sensors, are available on site. So many of the wearables, the sensors that are on robots, drones that actually can give you overall view. Our thinking actually is where we can actually leverage these data as well, because like with the help of mobile sensors, you can actually do measurements occasionally in areas that you might not be able to install a fixed sensor. And that actually is a good opportunity. And you're seeking some options there. And the other thing that we found is actually how you would visualize those complex data. And we think actually with the rise of these novel technologies like hologram tables or the VR, AR, or 3D immersive technologies, we can actually find pathways that actually we can present the data instead of form of graphs. We can actually present them more in a way that actually it can be understood by a human being. And I think that's another opportunity that we are looking at. So to close off, I would like to acknowledge the support that we get from the University of Queensland to develop some of these research. Also, JK Tech that actually they facilitate this webinar, but also they provide us with a great financial support that actually help us to develop these research, as well as the JK administration team for trusting in JKMRC administration team for helping us, and as well as JKT consultant that actually always they provide us with good technical input and support that actually we need, which is very important for us. With that, I would like to thank everybody for listening to me. I will look into some of the question. I know that actually there was one in the chat, in the question. Feel free to put, I got already one question, but feel free to put in your question. We got still a few more minutes to cover if you have any question. I'm going to read that one and answer it, but think about your questions. And if you are interested to know more or have some ideas or thoughts or discussion, feel free to reach out to me. I'm always happy to, if you're in Brisbane or Australia, have a coffee with you and have a chat, or talk to you online, or meet you and answer you on email. So I'm going to go through the first question. I'm hoping that actually I get lots of questions. So the question is, what do you do when the MPC breaks? Haha, yes, correct. Operations outside its envelope. And I think that's where it comes into how you developed your model and how you set your boundaries, because you can actually use the MPC within those boundaries and make sure that actually it works. And then we can start essentially putting some protection in terms of when it is operating outside those boundaries, have pathways or strategies that could essentially decide how to bring that process within that boundary. Because normally, if the operation is outside the envelope, it means that actually it's outside that optimum zone as well. And we have to think about, okay, what are the pathways that actually can bring it back? Again, to make a bit of an advertisement about the subsensor, I think the subsensor also have a good way to diagnose and know why the operation is outside its envelope. So then it can help you to refine that pathway. But I think, in my view, is you need to have pathways when the system goes outside the boundary to bring it back within the boundary by knowing what are the potential reasons behind that, and then you can start basically doing that. And they say if you have a faulty sensor misleading the MPC and neural net, which is a perfect question. I think I answered that to some extent. Essentially, I believe that actually, yes, we cannot trust the data purely, because if the sensor is faulty, it's going to mislead your MPC or neural network. And that is why we can leverage the power of soft sensors in a form that actually it can use it in the form of sensor fusion to cross-validate the data and provide a real-time, essentially accurate estimation. And if the subsensors pick up that the sensor is wrong, or there is a potential issue with the sensor, then we can start essentially using that understanding in terms of either setting or safeguarding that MPC, or even also by, which is coming in the future, by knowing the level of accuracy that you have in your data, you might be able to actually change the way that the decisions are made in your MPC as well, which could be a valuable thing. And believe me, I think one of the key points that I'm trying to push in the industry is developing these sensor fusion aspects is not that hard as well. And you can pretty much develop many of them. And because it doesn't involve any hardware development, I think that's the value in there. You can actually then ensure that you got a pathway for checking the accuracy of your data or consistency of your data. One example that I always give to people, most sites, you measure the current in the motor that drives the conveyor belt. And if it's your feed conveyor belt and you have a weightometer on that one as well, simply by putting a model that already we have developed in JK, and there are many of them out there, model of your conveyor belt, knowing the length, design of the conveyor belt, as well as correlating with the current that your motor takes, you can actually put a simple model there that actually estimates what's the mass on top of your conveyor belt. And that's a very good cross-validation against your weightometer. So you can actually cross-validate them and pick up whether, and usually that happens with the weightometer rather than the current that your motor draws, essentially is whether the motor is off calibration or not. And you can pretty much do many of these ones if you think about your process across many other points. And we got lots of great process models actually we can use it that for. And then, okay, and then there was another question there. I've seen some managers in the industry that say, we just get the best MPC. The money can buy, and we don't need to train our operators. May not be the best approach. May not be the best approach, yeah? On the day when MPC or even supervisory control doesn't work, you have even supervisory control doesn't work, you wish you had a trained, skilled, and experienced operator that could, yeah. I think you saw in my presentation, we cannot go with that approach in terms of only relying on automated systems. And I certainly not agree with that as well. And I believe that actually having good operators are important. But my thinking actually is, as you can see, like the industry now is heavily facing skill shortage as well. And this is not about because people, they don't want to come to our industry solely because of that. It's because the workforce are actually reducing as well. And not many people, they want to, essentially, they have other areas that actually can go because of the level of competition. So to me is, we can actually leverage the power of automation and do many of the low-level work that is need to be done. And then we can use our experienced people actually at a high level. And by the time that they see these automated systems, they are not performing the way that they should do, they can intervene and essentially help them to get to that level of work. I'm certainly agree with your point in that sense, in terms of the money and getting and buying the best MPC is not going to get you where you want. You need those level of operators as well. And to me, the fusion of essentially good operators with AI, machine learning, and advanced control is the pathway. So I answered that question. I don't see other questions coming in, but happy if there's any more question. Don't see it certainly in the chat box any questions as well. So, and I think pretty much we are on mark as well. So if there is no more question, I want to thank you everybody for joining the webinar, and I will pass it to you.
Thank you very much, Mosen, for your presentation around process control for mineral processing engineers. It's very much appreciated. Also, a big thank you to all the people who have attended, particularly in all the different time zones around the world. We will be uploading this to YouTube, and if you scan the QR code in the top right there, you'll be able to contact Mosen directly. Thank you very much, Mosen. It's been great. Have a lovely day, everyone. Bye, everyone.
Bye-bye.